On powers of 10. This is recorded to celebrate the 10th anniversary of LibriVox. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Abai in April 2015. On Powers of 10 by W. P. White from Science, Volume 35, January 5th, 1912. For expressing numerically the widely varying magnitudes occurring in scientific work, two methods are in common use. Both are adequate and accurate, but results expressed by means of one are much more easily grasped and remembered than with the other. The more convenient method appears to be gaining in use. The present paper is written with the idea that this desirable change may be accelerated if the advantages of the method are stated and thus presented to those who have hitherto not given the matter special attention. The simplest way of writing a number is, of course, to write it out in Arabic notation. But this, in general, involves the presence of numerous ciphers, which the reader must count in order to learn what the number is. There is, therefore, a gain if the writer counts the ciphers for him and records the number obtained. Hence the familiar system where a number is given as the product of 1, a series of significant digits, and 2, 10, with an exponent. For example, the velocity of light is 3 times 10 to the 10 centimeters per second. This system has still one great disadvantage. It calls in each case for the reading of two numbers, and thus greatly increases the strain on both the attention and the memory. And this difficulty is multiplied when the quantity expressed is less than unity, as it is about half the time. For then the exponent is negative, and the two numbers affect the resultant magnitude in opposite ways. For instance, suppose a galvanometer which requires 3 times 10 to the minus 8 amperes to give unit deflections. How will its sensitiveness compare with that of one for which both indicating numbers are numerically larger, say 8 times 10 to the minus 9 amperes? The larger significant figure, 8, indicates a larger current, and therefore less sensitiveness. But the exponent 9, though also larger, indicates greater sensitiveness. Really, the second is about 4 times as sensitive as the first, but this fact is far from evident on a first reading. Yet this is a very simple case. If a reader should see an account of one of these instruments on a Friday, and of the other on, say, the next Wednesday, it would require unusually careful reading indeed to leave him with any definite idea of the relative sensitiveness. The difficulty of this system can also be well stated as follows. When a number of magnitudes, say diameters of small rods, is stated, sometimes in centimeters and sometimes in millimeters, it is evident that a good deal of unnecessary difficulty results, which can be avoided by sticking to one unit or the other. Now, between a millimeter and a centimeter, there is the same difference as between any two consecutive powers of 10. An unrestricted system of notation by powers of 10, therefore, amounts practically to an unnecessary multiplication of the number of working units. The remedy is obvious: to diminish the number of units. This is realized in the other system, which proceeds by steps of 1000 instead of 10. A further gain is sometimes secured by using prefixes instead of exponents to indicate the working units, since the combination of a word and a number is preferable to two numbers, each of which interferes with the apprehension of the other, and even more with its recollection. This system is perhaps seen at its best in the field of electricity, where, besides the units, ampere, ohm, volt, etc., The milliampere, millivolt, microampere, microvolt, kilowatt, megaohm, etc. are in common use, and have almost completely displaced the reckoning by powers of 10. The advantages of the system have been made available in stating galvanometer sensitiveness by the scheme proposed by Ayrton. The sensitiveness is simply put equal to the deflection produced by a unit current, usually the microampere. According to this scheme, the sensitiveness of one of the galvanometers mentioned above is 125, of the other 33. Here the difficulty of remembering or comparing the two quantities would seem to be reduced to the minimum. And this illustration gives a fair idea of the value of the general method. Under it, but one thing claims attention: a single number, which need never exceed 3 digits unless the accuracy attained calls for a larger number of significant figures. Such a number is relatively easy to comprehend and to remember. The unit needs almost no attention, since all magnitudes between which a comparison is likely to be desirable will be expressed either in the same unit, or else in units so far apart that no confusion will occur. This choice of units is, of course, the essential part of the method, and it, of course, can be realized under the form of the notation by powers of 10 by those to whom that form seems desirable. All that is necessary is that those powers of 10 shall be chosen which are also powers of 1000, so that the use of 10 to the 2, 10 to the 4, 10 to the 5, 10 to the 7, 10 to the -2, etc. is to be discontinued. But the use of the prefixes to denote the units seems decidedly preferable. The electrician who should be advised to abandon his microvolts and milliamperes and go back to volts times 10 to the power of -6, etc., would scarcely be profoundly impressed with the value of the advice. A few special points seem worth noticing in this connection. A single prefix to denote 10 to the power of -9 seems desirable. Until it appears, 10 to the power of -9 amperes, for instance, should of course be called a millimicroampere. Micro of course means a millionth of a millionth, or 10 to the -12, or 10 to the power of -12, and is illogical when used for 10 to the power of -9, besides being less euphonious than the other. But it may be too late to stop the illogical use of mu for the millimicron, mu, in the domain of optics. There will undoubtedly be a tendency, as reckoning by powers of 1000 comes more into use, for work in each particular line to be always expressed in the same derived unit. Here the advantage of a common unit more than compensates for the fact that in some particular cases the unit is not quite the most convenient. For instance, workers with thermo elements have generally found it advantageous to work in microvolts, and to keep to this unit even when the number of microvolts is over 10,000, that is, more than 10 millivolts. In case of doubt between two units, it is probably better to use the smaller. For this diminishes the use of fractions, and also gives records more likely to be concordant with future work, since the increase of accuracy as time goes on increases the advantage of the lower unit. In no class of quantities is more to be gained by reckoning by powers of 1000 than with coefficients of expansion, and temperature and pressure coefficients generally. If these quantities were always tabulated in thousandths or millionths, instead of with a variable number of zeros, according to the fancy or convenience of the tabulator, a very much larger number of them would actually lie in the memory of the average working experimenter than are now to be found there. Yet these quantities, and some others, being pure numbers, have no special name, and therefore nothing to which the prefixes milli, micro, etc. can be attached. They may legitimately be designated as parts per mill, parts per million, etc., But these expressions are rather awkward, particularly when the whole expression is parts per mil per degree, or something like that. It would be convenient to use the fractional prefixes alone as nouns in such cases, milli meaning 1 part per thousand, and micro 1 part per million. There is certainly considerable reason to wish that some leader or committee, having sufficient authority, would authorize the use in this way of these terms, or something better. They have these advantages: they are brief, they would harmonize with the terms used for other physical quantities, they would tend to extend the use of powers of 1000. For instance, at present, most observers working to an accuracy of, say, 10 parts per million would prefer to state it as 1 part per 100,000, while with the word micro in use the almost universal expression would be 10 micros. And the use of powers of 1000 is quite as desirable in stating errors, etc., as in most other cases. The use of fractional or multiple prefixes also sounds a little strange in those cases where, in order to adhere strictly to the CGS system, the centimeter is used as the unit of all linear measurements. The real difficulty here, however, does not lie in the prefixes, but in the fact that two different fundamental units, the meter and centimeter, are in use, and that most physicists are probably more used to measuring small lengths in millimeters and microns. This difficulty would not be increased by the use of the term millicentimeter and microcentimeter, which are of course the logical terms to use if the centimeter is to become the practical unit of all lengths. It also seems logical to use the centimeter only where such other CGS units as the absolute electrostatic and electromagnetic units would be used, and to use the millimeter and micron in cases corresponding to those where the ampere, ohm, and volt would be considered appropriate. In any case, it may be well to repeat: the main and essential advantage of the newer system that is coming into use is in the restriction of notation to powers of 10 which are also powers of 1000. And this restriction can profitably be adopted whatever may be thought or done regarding the other points mentioned in this paper. W. P. White, Geophysical Laboratory, Carnegie Institution of Washington, Washington, D.C., November 1st, 1911. End of On Powers of 10 by W. P. White.